Hello and welcome again to the Theories of Everything program. I'm David Tao. This is the first in our new series, Theories of Energy. In our previous program we examined the explosive expansion of the internet, which will distribute information right across the planet and to most of its inhabitants. But to power that internet we also need energy. We need electricity, we need light energy as well. So apart from our new information requirements, the whole of our civilization is going through an exponential increase in power requirements. There are power grids being built across America, across Europe and across Asia. And there are many areas, for example India and China, that haven't really begun to expand their power requirements. So, where will all this power come from? Where will all this energy come from? This is what we'll examine in this first program. Let's examine the different roles of energy. First of all, life requires it to survive. Secondly, our whole industrial manufacturing production complex requires it to produce all the goods and services that we see around us. And thirdly, we need it for heating and also for cooling, because life, ironically, because of global warming, is going to be impacted by more severe fluctuations in climate. So there'll be a greater need for heating and cooling support. Fourthly, we need it for transport. But let's go back to the beginnings of human civilization on Earth. Let's go back perhaps 1 million or 2 years ago, when earlier hominids probably learnt to manage fire to some extent. They'd seen fire, of course, from lightning strikes, and they'd no doubt learnt that fire can be very valuable. Fire can be valuable for heating, fire can be valuable for cooking foods that would otherwise be too tough or inedible, and fire is also very good for keeping wild animals at bay. So probably they learnt to be able to conserve fire and to transport it with them, or transport it to even trade it with other tribes. And then about 150,000 years ago, modern humans emerged from the Rift Valley in Africa, probably around about that time, and they had already started to develop the use of tools. Earlier hominids had used tools, but modern humans probably learnt to use more advanced tools, double-edged axes, and more sophisticated flints. They, at this stage, their ability to use power was limited to themselves as individuals or groups, and each person generates about 1/4 of a horsepower. However, with tools and weapons, such as spears and clubs and so forth, probably they raised that level of power, they probably doubled it to about 1/2 a horsepower. But those tools and weapons were extremely valuable because from those early beginnings, humans learnt to manufacture more sophisticated artefacts. Now also, fire was also valuable in conserving regions for hunting. For example, early Aboriginal societies in Australia amongst them, learnt to use fire to burn in mosaic patches so as to regenerate growth and to make it easier for hunting animals. So we see that combining fire with weapons, humans had started to use power to their benefit quite substantially. However, the use of power and energy really took off around about 6,000 years ago with the emergence of cities, modern towns and modern cities. Cities required, of course, a great deal more building and a great deal more sophisticated techniques to raise weights, to move large objects around. So at this stage we can see the early development of levers, pulleys, cranes and so forth, which raised the power capacity of humans quite substantially. We look at structures like Stonehenge, for example, and see that to move those stones, huge boulders, perhaps up to 50 tonnes, required more than just straight manpower. Also, there was a stratification of society at that time into the landowners, if you like, the owners of property, and those who worked for them. In fact, there were many civilisations and most civilisations had a strata of slaves, so large numbers of humans could be applied to these sorts of tasks, including the structures such as Stonehenge, but also the Great Pyramids of Egypt. And also there were pyramid-type structures in all societies, all early societies right across the world, including civilisations in South America, Mexico, as well as in Europe. So we see that by this time, by about 5,000–6,000 years ago, the horsepower capabilities of humans had increased considerably. And of course the other area which had enabled them to leverage on their knowledge, if you like, was the domestication of animals. Horses, oxen, etc. were applied to agriculture. And this was quite a vital part of civilization's development. Without domesticating these animals, without being able to apply their energy, and adding their energy to human energy and human artefacts such as pulleys and levers, etc., civilization would have been much slower in its advance. So we fast forward to the 18th century, to the Industrial Revolution. In the meantime, humans had discovered how to smelt copper and to combine it with tin to make bronze. But in the 18th century, they learnt to purify a far harder metal, iron. And this laid the foundation for the industrial age, as did the development of the steam engine by James Watt. Now, this also began the use of fossil fuels on a large scale, because to smelt iron required a lot of charcoal, a lot of wood. So we find a lot of Europe's woodlands and forests being cleared. Now, during the clearing, of course, the other problem was that the ability to use wood was very expensive. The cost of using wood was very expensive, and it took an invention to use coal. The use of coal was substituted for wood around this time, and it was substituted through an initial process that produced coke, an initial process of burning coal in the absence of air to produce coke, and that coke could then supply the same energy requirements as the charcoal. So that did diminish the amount of woodland being cleared and provided a much cheaper method of producing iron, but it did produce more pollution, because coal, when it burns, produces all sorts of oxides, noxious oxides, not just carbon dioxide, carbon monoxide, sulfur oxides, nitrogen oxides. And thus began the pollution of our planet, certainly the pollution of the major cities in Europe. The industrial age was predicated on the theories of Newton to a large extent. Newton developed theories relating to the action of forces on particles, the resultant accelerations, the linkage with the relationship with mass, etc. This laid the foundation for the theory of machines. This, of course, was developed further in the 19th century by scientists such as Boltzmann, who developed their theories of thermodynamics, which is, instead of actions on individual particles, it was a process of statistical mathematics in which the actions on large numbers of particles, in other words gases, fluids, etc., the theory behind that was developed. And that paved the way again for future developments and more refinements in the field of machines. However, also in the 19th century, scientists such as Faraday and particularly Maxwell developed electromagnetic theory. That provided the basis for electric motors and all the electricity power grids and infrastructure that we see today. So in the 19th century, the power capacity of humans and human civilization went up another notch. It went up by a vast amount, in fact, because electric motors were able to perform and be available much more flexibly than steam engines. So electric motors were applied to every form of transport, and of course eventually the combustion engine for cars was developed. And so by the 20th century we have the usage of energy had increased greatly through the use of internal combustion engines, through the use of electric power, and still the use of steam. Midway through the 20th century, a new power source emerged, nuclear power. Based on Einstein's early theories, remember energy equals mc squared, the relationship between mass and energy. Only this time the energy was 1,000,000 times greater than the energy produced by oxidation, by combustion, the energy produced by fire, for example. So nuclear energy was fantastic, and it had the potential to produce enormous amounts of power, but of course we know the downsides now. And every energy source had its downsides. By the 1950s, the problem of pollution was becoming apparent. And of course, it was also becoming apparent that nuclear fuels were, once used in power stations, still retain dangerous properties for thousands and thousands of years. And later we learnt that there were, with the accidents that happened at 3 Mile Island and elsewhere, we learnt the real problems of nuclear fuel and nuclear power generation had the potential to obliterate everyone on the planet, especially if used in weapon form. Now, each time humans had to learn to manage these new power sources. In a future program I'll be discussing nuclear fuel again and the new approaches to its use, the new safe approaches. At the same time, the burning of coal. There's a lot of research going into the burning of coal to make it safer, to remove dangerous oxides and to remove a lot of the pollution, a lot of the unburnt hydrocarbons that produce smog, and also the use in transport of producing cleaner fuels to avoid some of that smog as well. So as we go along, these power sources are still being used, but we have to expend a lot of energy, a lot of time, a lot of effort into learning how to use them safely. And of course, there's still a lot of risk involved, and we'll be discussing that again in later programs in this series. Let's look a little further into now the 21st century. In the 21st century, it's become clear that we need a new mix of power sources, as well as fossil fuels, as well as nuclear energy. We're going to need to take advantage of all the other potential sources that are now being developed and already are in production in many cases, such as solar power, of course, wind power, wave power, etc. Now, energy from these sources is already being fed into national power grids in Australia, but also overseas, in the US and in Europe. There are a number of wind farms, for example, which have large turbines in usually very windy areas, that are feeding probably around about 1% of energy into their national grids. Wave power is fairly new, but solar energy isn't. Solar energy has now been around for a long time and provides heating to a lot of homes, and very cheap heating as well. So we can see that this new mix is beginning, and these new cleaner renewable sources of fuel are starting to not only be applied but be accepted by oil companies and by power companies, and they're also becoming very prominent in the mind of the general population, because there's an increasing awareness that if we don't use clean renewable sources of energy, the whole of our planet, the whole of our civilization is at risk. Looking into the future of the third millennium and beyond is very exciting, because there are some tremendously interesting new power sources just starting to edge into the research laboratories. For example, there's fusion, nuclear fusion, which doesn't produce the dangerous byproducts of nuclear fission. Nuclear fusion, of course, powers the sun, and it powers all the stars as well. And no doubt, probably in the next 500 years, there'll be efforts made to tap directly into this major source of energy. And the reason we'll need these other sources of energy will be because civilization's growth will continue. The needs of its infrastructure, it won't stop. Beyond the Earth, of course, we're already exploring other planet systems. And there'll be the mining of some of those planets, there'll be the application of civilization on those planets, and beyond our own solar system we'll move to other star systems. It sounds a little futuristic, but I think if you look at the progress of human civilization, or at the exploration efforts of human civilization, you'll see that they moved from a small area around the Mediterranean. They next tackled the oceans. We've learnt to go into space. We've sent probes to Mars. We've sent probes to the outermost area of the solar system. So this process will continue, and it will demand vast amounts of energy. Now, this energy will not only come from tapping directly into the sun's source, but it will eventually come through more sophisticated uses of gravity, for example. We already use gravity to slingshot probes around the solar system to take advantage of the enormous amounts of energy that gravity provides. In the future, of course, we'll be in Star Trek territory, and no doubt we'll use gravity, we'll use forms of mastering space-time to travel to distant places. This is very futuristic, but it's worth just mentioning. Because, again, if it's one thing we've learned, it's that humans never stop. They keep on going, and our civilization will continue, and its exploration will continue of far systems. Eventually, of course, the ultimate energy source will be applied, and that will probably be in another couple of thousand years. The energy source of black holes. Black holes can acquire, can absorb, in fact, billions of suns. No one quite knows what happens to the energy that goes into black holes. Some say it comes out the back in the form of other universes. But basically it is the ultimate source of energy. And again, probably in several thousand years, that is a source that humankind will tap into. Returning to the present, let's see what our current needs are. Our current energy needs include, again, heating and cooling, and they include transport, they include energy needed to power industry, and all the services such as attached to the internet, for example. We use up around about 1 million billion kilojoules per day of energy, or around about 10 million tonnes of oil a day, or about 10 billion litres of oil. Not all of this comes from oil, of course. About 40% comes from oil, and a large proportion of the rest comes from coal and natural gas, and the rest is generated from the other alternate sources of energy that I mentioned, from nuclear energy and from the renewable sources such as solar, wind and wave energy. Now let's begin with the fossil fuels. We're burning those up at an amazing rate. We still have large reserves. Due to more sophisticated geophysical techniques, exploration techniques, new oil basins are still becoming discovered. Still being discovered in places like the Caspian Sea, the Black Sea, and this is one of the new sources of oil. As most of us have followed from the political situation, wherever oil is, then the great powers will follow and exploit that resource. But it is finite, and there's no doubt about it that probably within about 50 or 100 years that resource will be used up if its current rate of consumption continues. But then we have also probably 1 trillion tonnes of recoverable coal. And that's a large energy source, and as mentioned, it's been used since, well, at least since the 18th century in large amounts. So that produces a lot of pollution, but again, as I mentioned, the research is continuing to improve that, to improve the use of coal. In fact, the third area of fossil fuel is gas. Now, gas is the common name, if you like, for methane. It's actually a mixture of gases. It's a mixture of methane, ethane, propane and butane, but 95% comes from methane, 1 atom of carbon and 4 atoms of hydrogen. And because there is only 1 atom of carbon, you can break that bond quite easily and release quite a reasonable amount of energy. So this is probably, after oil, the main source of our energy. Methane powers, or gas powers, a large number of power stations. So we have those three major groups of fossil fuels, except that methane is not just a fossil fuel, but it's a renewable fuel as well. Wherever you can generate it from waste, you can generate it from organic matter, providing that organic matter is closed off from the air, so that anaerobic bacteria can produce the methane. So it's a form of biofuel which is used now widely across Europe in small to power the fuel needs of homes at a domestic level, and of course, as I said, it also powers is the major energy source for many of today's power stations as well. So those three are very important, but also because oil is a finite resource, we need to provide potential substitutes for it. Brazil, for example, decided it could substitute at a reasonable price ethanol, which can be made from the fermentation of sugar, which is grown in large amounts in Brazil, and that could provide an alternative fuel for cars. And they did this. They have about 5 million cars. When the price of oil went down, it couldn't compete on a price basis, but its only byproduct its main byproduct is again carbon dioxide and water. So it's also a clean fuel and much cleaner than petrol, and therefore their cities are comparatively unpolluted, even though they're huge today. But they couldn't compete on price with cheaper oil once the price went down, so today it's used, usually mixtures of ethanol and petrol are combined, and ethanol and its sister product methanol are used to produce lead-free petrol throughout the world. As well as substitutes for petrol, such as ethanol, there are also now substitutes for diesel fuel, generated from grain crops in the US, such as corn, and also from rapeseed oil in Europe. Algae, of course, also can produce 50% of its weight in the form of oil. 1 hectare pond of algae can generate around about 120 tonnes of algae, and 50% of that is oil. So these alternatives are available. They're a little pricey at the moment, but they're there for the future. As well as that, I mentioned methane before, and methane, or gas, which is used, of course, in a large number of cars today, is generated generally from oil deposits, but also it can be generated, it's stored in vast quantities, trillions and trillions, in fact, of cubic metres of methane are stored in the form of hydrates, gas hydrates, on the ocean floors, for example, and about 12% by weight of those hydrates are methane. Just incidentally, viewers, it does have a link, the fact that hydrates are available that store this gas, does have a link with mythology, with the mythologies of the Bermuda Triangle. It's thought that when planes fall out of the sky in this area, or have fallen out perhaps, or disappeared, it could have been because of vast quantities of methane gas coming to the surface and flowing upwards, and of course methane doesn't have the support capability that air does, and the plane would have plummeted straight down. Also ships would have too, straight through the water, because of the plume of this gas generated perhaps by some disturbance in the ocean floor, some earthquake. So we see, viewers, at the beginning of the 21st century, that humans have a choice between a large number of different power sources. They have fossil fuels on the one hand, which is coal and oil and gas, basically methane. They are starting to dabble in the alternate clean sources, solar energy, wave power and wind power. They also we've been badly affected in the past by nuclear power, but that energy source is starting to become more sophisticated and perhaps cleaner and safer in the future. We're at the crossroads, really. The social drivers for our choice of fuels is more and more predominantly fuels which can avoid this greenhouse effect, which is very close to being a runaway effect. We need to make our choices very carefully from now on, and I think everyone's aware of that. So in the future, that's why we have, for example, the Kyoto Agreement. The only countries that haven't signed up to the Kyoto Agreement are, well, two of them are Australia and the US. The Kyoto Agreement says that we should return our energy usage back to 1990 levels by the year around about 2008. We should also, and also implemented will be a mechanism of carbon credits, so that countries that use less than that can trade that with countries that use more, so that the overall effect is limited to that 1990 usage level. But that's really just a beginning. So in our future programs, we'll be discussing some of the more esoteric energies, sources, including nuclear energy, but also the new renewable energy sources, and finally some of the sources that may power our starships beyond this solar system. I'm David Tao, and you've been watching again the Theories of Everything program. I'll look forward to seeing you again next week.